little -1. That just means inverse. That's not raised to the -1 power. It's just a label. It's just how you note that that is the inverse of the regular function is f of x. The inverse is f to the -1 of x. Okay. But that -1 is not used in any calculations at all. All right. And so the way we find the inverse is first, we know that f of x is the same thing as y, right?
Yeah.
F of x is y, right? And so we replace the f of x with y first. Then you switch your x and y and solve for y again. What your y ends up equaling is the inverse of the original function. Okay, it's the opposite of the function. And so if you were given just a table, okay, this is x and y, right? X is -2, 4, -1, 2, 0, 0, 1. Okay, so these are your coordinates for x and y coordinates. If that's the original relation f of x, then the inverse is those switched around. Instead of -2, 4, it's 4, -2. Instead of -1, 2, it's 2, -1. Those x's and y's are reversed. Okay, so this would be, as far as what a table looks like, that is what the table of the inverse would look like. Okay, those x's and y's are just reversed. Okay, so if they gave you coordinates, if they gave you these coordinates and they said find the inverse, all you have to do is reverse the x's and y's. And that's what these are. Okay, so remember, it's x and then y, x and then y. So if it's 3, -2, then it would be -2, 3. Those x's and y's are just simply reversed. You need to keep this in mind because when we start graphing the original equations, if we go look at the table, we can identify whether two equations are inverses of each other by looking at the table, because those x's and y's of the inverse will be the opposite of what the original one was. Okay, so in this first example, you have to find the inverse function. They give us the original function, we have to find the inverse. Now, I said the first thing you do, now once we actually find the inverse, I'm going to come back and I'm going to write it right here, okay? And so, this is our original function, okay? So we have y equals 2 over x plus 1, then minus 2. That's my original function, right? Okay, so what we do now is we switch the x and y, literally. So instead of y, I put x equals 2 over y plus 1 minus 2. You switch the x and the y. And now we're going to solve for y. What y ends up equaling will be the inverse. Okay? Now, this just requires your algebra skills on what you need to do to get that variable by itself. Okay? And so, we need to solve for y. So the first thing I need to do is I need to remember, this is together, right? Okay, so I need to get this y out of that denominator. Any suggestions?
Times x by 2.
I can't, no. First thing, this is minus 2, right?
Yeah.
Okay, I need to add 2 to both sides so that I get this fraction by itself. Okay, so that's going to be x plus 2 equals 2 over y plus 1. Okay, now do what? Multiply both sides by y plus 1. That'll get that y plus 1 out of that denominator, right? Okay, we did that in our last section. Okay, and so remember that x plus 2 is together also. So when I multiply both sides by y plus 1, I end up with y plus 1 times x plus 2 equals 2. Right? Does everybody see that? Multiply both sides by y plus 1, and this y plus 1 will cancel right here. Everybody see that?
Yes.
Okay. So now, all I need to do is distribute all of this so that I can get y by itself. Actually, I'm not going to distribute it because that would do more harm than good. If I distribute the y, then I'll end up with xy plus 2y, and that doesn't help me get y by itself, right? So what can I do? Divide by what?
X plus 2.
Very good. Now if I divide both sides by x plus 2, I'll end up with y plus 1 by itself. Everybody see that? Everybody see that?
But that just ends up.
No, it doesn't. Look, so if I divide both sides by x plus 2, that cancels, right? So now I have y plus 1 equals 2 over x plus 2. I almost have y by itself. What do I do?
Subtract by 1.
Subtract 1 from both sides and I'm done.
You do it.
If I subtract 1 from both sides, I'll be done. Okay, so if I subtract 1, I end up with y equals 2 over x plus 2 minus 1. That is my inverse function. You could put a little -1 up there. That's just a way to label that as the inverse of y.
Okay.
So we solved for y. What we did was, let's go over what we did. First, this was my original function, okay? And then I switched the x and y. And then I needed to just manipulate this so that I ended up with y by itself. So first thing I did was I moved the 2 to the other side. So that gave me plus 2. Then I multiplied both sides by y plus 1 to eliminate this y plus 1 in the denominator.
Wait, pause. Yeah, hold up.
Okay, so we multiplied both sides by y plus 1, and that got y plus 1 out of the denominator. Then we divided both sides by x plus 2 to get y plus 1 by itself, right? And then to get y by itself, we just subtracted 1 from both sides.
It's not that. It's just a lot of stuff.
It's just mathematical manipulation,
I just don't want to
okay?
do this.
And so the inverse is 2 over x plus 2 minus 1. So the original function was 2. This was the original function that they gave us. This was the inverse that we found. Okay, let's do this one together. Okay? Yes. Okay, so first thing I need to do is I need to write the actual original y, right? So this is, okay, so our original is, this is y, right? That's y.
Yes.
So y equals negative cube root of x plus 1. So I didn't switch anything yet. I just wrote the y. Okay, that's the original one. Now, what do I do next?
You switch it.
Switch the x and y. Switch the x and y, and then solve for y. Okay? So this is now x equals negative cube root of y plus 1. Now, plus 1 is not underneath that radical. Yes?
How come you wouldn't like combine the x with the cube root? Like, how come you wouldn't take all of that over?
Okay. So, now we need to solve for y. We need to get y by itself. What's the first thing I do?
Take one.
Subtract 1 from both sides, right? So that'll be x minus 1 equals negative cube root of y. What do I do next?
You every
Divide by negative 1. It's just like if there was a 2 on the outside. I'd divide both sides by 2, right? So we divide by negative 1. Now, when I divide everything by negative 1, this becomes positive, right? But dividing these by negative 1 just changes these signs, right? So this becomes negative x plus 1. When I divide everything by negative 1, it just changes the signs of everything, okay? And so now I have the cube root of y. I don't want the cube root of y, I just want y. What do? I have to cube it. I have to raise it to the third power. Just like when we have the square root, to get rid of that radical, we square it, right? Yes. Yes. Because it changed this to negative x and changed this to positive 1. Dividing everything by negative 1 changed all those signs. Sorry. I guess I shouldn't have skipped that. Okay. Okay, so in order for us to get rid of this radical, if we have the cube root, we have to cube it. So we have to raise it to the third power. But if I raise the right side to the third power, I have to raise the whole left side to the third power. Now, good news. We're not going to expand that and distribute everything. We're just going to leave it like that. We're going to leave it negative x plus 1 to the third power equals y. That is your inverse. So all I'm going to do next is I'm going to go fill in that blank at the top where it said y to the negative 1 of x. That's the inverse of y equals, because this is the inverse. Okay? Equals negative x plus 1 to the third power. Okay, we moved the 1 to the other side and it became minus 1. All right? And then we divided everything by negative 1 to get rid of this negative right here. Okay? And then we cubed everything to get rid of that cube root. If it was the fifth root, we would raise everything to the fifth power.
I'm lost.
Okay?
Okay, you said.
Now, these problems say verify that f of x equals 2x minus 4. And what does this mean?
Inverse.
And the inverse is this. Verify that they are inverses. Now, any suggestions on what we can do? Verify means prove. How can I prove that these are inverses? I can work one out and make sure it equals the other. Okay, that's going to be method 2. Method 1, let's work it out, and verify means prove. We're going to prove that they are inverses.
Which one would be easier to work out?
Well, I would start with f of x. I would do this one, and then prove that its inverse is this. Okay, so we have y equals 2x minus 4. Okay, what do I do next? Switch the x and y. I didn't switch them yet. This is the original one. Remember, that's y. And so x equals 2y minus 4. Okay? I need y by itself. What do I do first? Move the 4 over and it becomes plus 4. So that's x plus 4 equals 2y. Okay, now what? Divide. I have to divide everything by 2. When you multiply or divide in an equation, you have to multiply or divide every term by that. Not just one time on the left and one time on the right. That's what you do with addition and subtraction. With multiplication and division, every term has to be multiplied or divided. So, I'm going to multiply this by 2, but that means I'm going to multiply that by 2 and that by 2 also.
So you're dividing them.
I mean, divide. Very good. Thank you. Divide. Okay? So, x over 2, that's the same thing as 1/2 times x. And 4 over 2 is just 2. So this represents the inverse, right? So I'm going to put my name tag. That means inverse. So is it the same thing?
Yes.
Yes.
Wait. Can you go back down, please? Wait. I have negative 4 for some reason.
Okay, so we proved that they are inverses. Okay, so it might give you f of x and give you f negative 1 of x and say, are they inverses, yes or no? So you can take the original and find the inverse and see if it matches the inverse that they told you. Another way to do it would be what? Put this one in the calculator as y1. Put this one in the calculator as y2. And then we can look at the table. How will looking at the table help us figure out if they're inverses?
They will match up perfectly.
They're not going to match up perfectly. If they match up perfectly, there will be the opposite.
Because
The x's and y's have to be reversed. Now, sometimes when you look in this calculator, when you bring up the table, it's going to say x. The x is going to be the same for both. It's going to say x and it's going to say y1 and y2. So looking at this table, you have to be careful. You need the x's and y's for y2 to be reversed, to be the opposite of what they are for y1. So when we put these, I want you to do that. I want you to put these in your calculator as y1 and y2.
Come on now.
Okay, so f of x is, y1 is 2x minus 4. And the inverse was 1/2 x plus 2. Get used to using that fraction button, because you need to just get used to using that, okay? And so when you put these in, we're going to look at those tables and show that the tables represent the inverses. That means every x and y1 has to be reversed for x and y2. Okay? And so sometimes it's easier to see if you put it on a regular table. Okay? And so when we look at this, this is y1 and this is y2. Okay? For y1, now the x values, let's look at 0, 1, and 2. 0, 1, and 2. Does everybody have their table up?
Yes.
Okay, so for y1, x is 0. What's y1? Negative 4. Okay? And then x is 1, and what's y1? And then x is 2, and what's y2?
0.
I mean y1, 0. Okay, now, you need to look at, now we're not looking at the y1 column anymore, we're only looking at x and y2. If they're inverses, these are going to be the opposite. When x is negative 4, y2 should be 0. Do you understand? This should be what your table looks like for y2. So you have to go to negative 4 on x, and y2 should be 0.
That is crazy.
They're the opposite, but when they put all three columns together, sometimes it's difficult to follow. And so instead of 1, negative 2, it should be negative 2, 1. And instead of 2, 0, it should be 0, 2.
It is.
And it is. Now, this skill that you're doing right now, looking at this table and verifying their inverses, is going to be valuable when this final exam comes. Because they're not going to be a simple problem as 2x minus 4 and the inverse is this. It could be some big complicated mess that if you had to actually algebraically find the inverse, you might get stuck on some steps and can't figure it out. But if all you're doing is seeing which one is the inverse, A, B, C, or D, you put the original one they gave you in as y1, put option A in as y2, and check those tables and see if they're inverses without actually having to do the algebra. Do you understand what I'm saying? Okay, and so for each one that we do, I want you to go look at the table, and you're going to have some practice with this homework too, checking the table to see if they're inverses. Okay? And so basically you're going to look at the x value in y1. So if it's 0, negative 4, then go find negative 4 in the x column and see if y2 is 0. Okay? And so let's look at the next thing. The next thing is we learned when we looked at the algebra what a regular function and its inverse looks like algebraically. Y'all pay attention.
Come on, guys.
And then we learned what a regular function and its inverse looks like on the table. Okay? Well, what does a regular function and its inverse look like on a graph? Well, no. Everyone know what a reflection is? Okay. Okay, so a reflection, if you take a graph and you reflect it, it's like a mirror image of itself. And it's either reflected across the x-axis or the y-axis. So it's either, if this is the original function and it's reflected across the x-axis, it does this. Okay? If it's the original function and it's reflected across the y-axis, it does this. Okay? Well, a function and its inverse is reflected, but it's reflected across the line y equals x. And that's a straight diagonal line. Okay, so this is a picture of what a regular function and its inverse looks like. Okay, and so this green line is the line y equals x. That means every point on this line is 1, 1, 2, 2, 3, 3, 4, 4. So it's a diagonal line. So if it's every single time a function and its inverse is reflected across that line. So if it starts off like this, it's going to go like this. Do you understand? It's reflected. It's a mirror image across this diagonal line. So it went like this, and then it went like this. It's reflected across that line. It's not just reflected up and down or left and right. It's diagonal. Okay? And so, do y'all remember from Math 1 and Math 2, the vertical line test on how to tell if something's a function? Right? If you look at the graph and you draw a straight, verticals up and down, if you draw a straight line, if it doesn't touch that graph in more than one point, then it's a function. It passes the vertical line test if it only touches it at one point. No matter where you draw that vertical line. If it only touches it in one point, it passes. If it touches it in more than one point, it fails and it's not a function. Okay. Well, we use the vertical line test to tell if the graph is a function. We use a horizontal line test to tell if its inverse is the function. Now, what I'm saying is, without actually graphing the inverse, if you have the regular function, this blue graph right here, okay? The regular function is, you take it and we do the vertical line test. We see that it's a function, but if I do the horizontal line test, it fails, right? On the original function. Horizontal line test fails because it touches that in more than one point. So that means that its inverse is not a function. And I know that's true because when I'm actually looking at a graph of its inverse, does it pass the vertical line test? No, it doesn't pass the vertical line test. So if you had the graph of the inverse, you could just do the vertical line test. Is the inverse a function? No. But without having to go graph both of them, you can tell by just looking at a graph of the original function. Vertical line means it is a function. Horizontal line tells you whether its inverse is a function or not. Okay? So when we look at this graph right here, this is f of x. This is not the inverse. This is our regular function. We're going to do both tests to tell whether it's a function and whether its inverse is a function. So, is f of x a function?
Yes.
Yes, because it doesn't matter where I put this vertical line. Here's a vertical line, right? How many places is it touching that red graph? One. It's just touching the red graph at 1. We don't look at the x and y axis. They're not part of the actual graph, okay? I'm going to move it over. How many places is it touching it?
1.
1. Can I put it anywhere and make it touch it at more than one point?
No.
No. As long as it's a vertical line, it's never going to touch it at more than one point, regardless of where I put it. So it passes. So is f of x a function? Yes. Yes, it's a function. Now, let's see if its inverse is a function. Well, I don't have a graph of its inverse. I only have the original function. Well, that's okay. I can take this. Okay, so now, in order to tell if the inverse is a function without actually having a graph of the inverse, we can do a horizontal line test. And so, let's draw a horizontal line. That's a horizontal line, right? Okay, so let's do the horizontal line test. Does it pass? No. It touches that red graph here and here, so it fails. So that means that its inverse is not a function. Because you don't want to have to go through, and some of these graphs look crazy. You don't want to have to go through and actually try to reflect them across a diagonal line. That's difficult. But all you have to do is a horizontal line test to tell whether it's inverse of the function.
Where is it?
Does everybody understand? So we do a straight up and down vertical line test to tell whether that graph is a function. But we do the horizontal line, which meant inverse means opposite, right? So we do the opposite line test to tell whether its opposite is a function. Okay? Okay, this is what I said. Look at the instructions. What do the instructions say? Determine if the inverse of f is a function. So these are graphs of f. Okay? I don't even know what the equation looks like. All I know is the graph. What am I going to do?
The horizontal line.
Very good. I'm going to do a horizontal line test and see whether its inverse is a function. So when we look at the first one, does it pass?
Yes.
Does it still pass?
Yes.
Does it still pass?
Yes.
Does it still pass? Okay, that wasn't supposed to happen.
Yeah,
What about where?
What, the one?
The
Oh,
line.
no, never mind.
Well, it's still 1 point.
Yeah.
Here?
Yeah.
It doesn't matter.
It's still 1 point.
It's still only touching at one point. So, is its inverse a function?
Yes.
Yes.
No.
Now, for the second one, first of all, let me ask you this. Is it a function?
No.
Is it a function? It is a function. I can do a vertical line test and it passes. Is its inverse a function?
Okay.
No. It fails. So, her question was, so the vertical line test is just for the original? Yes. The horizontal line test is just for the inverse? Right.
Anything else?
Right. Okay, so two more examples of regular finding the inverse. Okay? For the first one, again, these steps are still going to be the same. First, I'm going to write the original problem. Y equals x to the third plus 2. Then I switch x and y, correct?
Yes.
So x equals y to the third plus 2.
Subtract 2 from both sides.
Good. Step 1, subtract 2 from both sides. So this is x minus 2 equals y to the third. Now, I heard somebody say you square root both sides. We don't square root, cube root.
That's what I meant.
No, this is y to the third. We need just y.
Oh, okay.
So if it's
I'm thinking.
cube, we need to take the cube root, okay? So, cube root. So y equals the cube root of x minus 2.
And that's it?
That's the inverse of that one.
Would there be an answer choice that is like that?
Now, what if I was taking the square root, Nate? What if I was taking the square root? What do you have to do? When you take the square root of both sides, you have to consider plus or minus. Okay? So, if there is an even root that you have to take of both sides, this was an odd root, so it doesn't matter, right? Something cubed can be either positive or negative, right? It doesn't matter. But if it's an even root, for example, to the fourth power, we're going to have to, at some point, take the fourth root of both sides, right? Which means you have to consider the plus or minus. They give you this piece of information to tell you which one is going to be your answer. Only one of them is going to be your answer. Thank you. Thank you. Okay, listen, guys, we're short on time. Okay, so let's work this problem. First, y equals 3x to the fourth. What do I do now? Switch the x and y. So x equals 3y to the fourth. Okay? I'm getting y by itself. Divide both sides by 3. So x over 3 equals y to the fourth. Now, we have to take the fourth root of both sides. Because it's the fourth root, because it's an even root, it's plus or minus, but you can't have two answers. Your inverse can only be either or. Okay? So this tells you which one is it going to be?
Minus.
The negative, because this says x has to be less than or equal to 0. If it was greater than, the answer would be the positive. Okay, so let's do it. So we have to take the fourth root of both sides. Nate. So that's plus or minus the fourth root of x over 3 equals y. Now, you can't have plus and minus, it only has to be one of them. So it's going to be the negative fourth root of x over 3 equals y.
Why didn't you do the plus or minus on the other side?
Because it was taking the third root. If it's odd, it doesn't matter.
Okay.
You don't have to consider positive or negative. Okay? But if it's even, if it's an even root, you do have to consider plus or minus. Because how do you know? Because when you look at x squared, if x is either positive or negative, the answer is the same. But if it's x to the third power, if it's the answers are different if it's positive or negative. So it doesn't matter.
I'm saying, how do you know for the second one you did? Okay, how do you know if it's negative? How do you know which one to pick?
Oh, I know which one to pick because it told me in the original problem right here.
Oh, okay.
That means you picked the negative one. So the answer was negative fourth root of x over 3.